An optimization problem is an application of calculus to a physical situation, where I want to make a certain quantity as large as possible or as small as possible. Here is an example. A woman gets on her boat at point A on one side of a straight river, which is 3 kilometers wide. She wants to get to point B, 8 kilometers downstream on the opposite side. She could row the boat directly across the river and then run for 8 kilometers, or she could row directly from A to B, or she could row to some intermediate point and then run. If she can row 6 kilometers per hour and run 8 kilometers per hour, where should she land to reach B as soon as possible? At this moment, I invite you to pause the video and try to solve the problem. Even if you cannot fully solve it, if you spend some time trying to get started, setting it up, drawing a picture and understanding what it means, my explanation will be much more useful. The first part of the problem is the modeling. We need to transform the word problem into a mathematical precise question. In this case, the question will be something like, I want to find the maximum or the minimum of this specific function on this specific domain. Let's draw a picture. We have a straight river, and the woman begins on one side of the river. Let's call this point A. We also know the width of the river is 3 kilometers, and she wants to row to some point on the other side. It's called B, and we know B is 8 kilometers downstream from A. Now, as the problem says, she could row straight and then run, or row directly to B, or most likely to some intermediate point. So the path she is going to take is probably rowing somewhere there, and then running all the way to B. The other information we have is that she rows at 6 kilometers per hour, and she runs at 8 kilometers per hour. And what we want to figure out is the position of this point here. So let me use a variable for it. I could do it in various ways. I could, for example, use this angle as the variable. I think it's going to be simpler to call x this distance, and that's what I want to figure out, what the value of x is. Now, we need an equation for the total time, because that's what I'm trying to minimize, the total time she spends moving from A to B. And I can say that the total time, well, it's going to be broken into the two parts of the trip. Let me give a name to this point. Let's say we call it C. The total time is the time from A to C plus the time from C to B. And now what I need is to write an explicit equation for each one of them. For that, I will need to know the value of the two distances C runs and rows. The distance from C to B is 8 minus x. As for the distance from A to C, I have a right triangle here. This side is 3, this side is x. So using Pythagoras' theorem, I know that this length is the square root of x squared plus 9. And I think now I have all the data I need. I can write the total time as follows. First, I need the time from A to C. Well, the distance is root x squared plus 9, and the velocity for rowing is 6 kilometers per hour. Therefore, the time will be the distance, root of x squared plus 9, over the velocity, 6. And then, to go from C to B, the time from C to B, is going to be the distance, 8 minus x, divided by the velocity for running, which is 8 kilometers per hour. And that's the total time. I should specify the domain. I cannot forget that. So the values of x have to be between 0 and 8. It wouldn't make sense to row to a point here to the left or to a point past B. So it's going to be between 0 and 8. And I definitely need to include the endpoints. I'm looking for the minimum of this function, and it could very well happen at 0, or it could very well happen at 8. Maybe those are the optimal ways to go. Also, and now I have it. This is the function I want to minimize in this domain. That completes the setup of the problem. The second part of the problem is easier. We just need to use calculus to find the minimum of this function. Before we jump happily into taking derivatives, I'd like to make an observation. This function is continuous, and the domain is a closed and bounded interval. It includes both endpoints. Therefore, I know, by using the extreme value theorem, that this function must have a minimum. And I know more. The minimum will either be a critical point, or it will be one of the endpoints. Therefore, all I have to do is find the critical points, find the endpoints, and compare them. And I'll be done. I don't need to do any more justification. But that is only because I could use the extreme value theorem, because the function was continuous and the domain included both endpoints. Well, I know what the endpoints are, so let's find the critical points. For that, I need to figure out what the derivative is. And now I need to figure out when the derivative is 0. So I will skip the details, do the algebra at your own pace, but after doing a bit of calculation, this function ends up having one single critical point, and the derivative is 0 exactly when x is 9 over root 7 kilometers. Now this is the only critical point inside the domain. There could be others outside the domain, but I don't care. I only care about what happens inside the domain. So I have my critical point, and I also have my two endpoints. So let's compare them. And as a comment, yes, we definitely need to use the endpoints. It's possible the minimum is there. For example, if the woman could row much faster than she could run, then definitely the optimal path would be to go directly from A to B, and the minimum would happen when x equals 8. And if the woman could run much faster than she could row, then definitely the optimal path would be to go from A straight here and then run all the way to B, and the minimum would happen at x equals 0. And I don't know what much faster means in this case. So it is possible the minimum is at an endpoint. And either way, in order to use the extreme value theorem, I definitely need to include the endpoints. So let's compare the 3 points, the 3 candidate points. Here they are. These are my 3 candidates. All I have to do is take these values of x and plug them back into the equation for t. Well, that requires a little bit of calculation. I'm going to skip the details and just give you the final result. When x equals 0, the time is 1.5 hours. When x equals 9 over root 7, after doing a little bit of algebra, the time is 1 plus root 7 over 8 hours, which is approximately 1.33 hours. And when x equals 8 kilometers, the time is root 73 over 6 hours, which is approximately 1.42 hours. And of all those 3, the smallest one is the one in the middle. Therefore, after all, the critical point is the one that matters. The minimum of this function occurs when x equals 9 over root 7 kilometers. And that's the answer to the problem.